Hello everyone. My name is Anthony Szego. I'm a student, a PhD student in the Department of Materials and Environmental Chemistry here at Stockholm University. My supervisor is Niklas Hedding, and I will give a brief talk about some work I've been doing on heterogeneous transformation of carbon dioxide to methanol, with an emphasis on the structural study of the support. Regarding why we want to make methanol, uh, there's this concept known as methanol economy, in which we try to find this cycle in which we can capture CO2 from the atmosphere, uh, and then through various ways we can try to convert it into something useful, ideally by using renewable sources of energy. And we can transform CO2 into methanol, which is a platform chemical that can then be used in the synthesis of plastics, different commodity chemicals. It's highly used as a solvent, and it's especially interesting in its use as a fuel. The use of the methanol as a fuel would then lead itself into forming more CO2 into the atmosphere that we could ideally recapture and reuse in this green sort of cycle. And we know that CO2, as mentioned in previous talks, is a big issue in the atmosphere because it's it causes global warming because it's a greenhouse gas. So it's one of the main impact factors in causing global warming. So if we find a way to capture it, use it in a cycle that would lead to negative carbon dioxide emissions, it would be a great step forward into trying to combat this apocalyptic future that seems to face us. So the system I'm working on is based on a homogeneous system. So the homogeneous system has two phases. There's an aqueous phase that contains amines dissolved in them, and then there's an organic phase that contains a ruthenium catalyst. The role of the aqueous phase is the capture of the CO2 through these dissolved amines. And then the ruthenium catalyst is the one that hydrogenates this captured CO2 into methanol. So the aim of my project was trying to heterogenize this homogeneous system. To do that, we started with some silica particle supports, and we modified them by grafting aminated silane monomer chains on its surface. So the roles of the aminated chains is the capture of the CO2. So there are solid adsorbents that are able to capture the CO2 and pre-concentrate them for the reaction, for the hydrogenation reaction. And the reaction is carried out by impregnated ruthenium catalysts on these modified supports. So in this slide, I show the ruthenium species that we're using as an active species. And then the modification was done with two different aminosilanes, one with a primary single amine and one with a secondary and a primary diamine. So I will refer to them as monoaminated modified silica support and diaminated modified silica support. So as I said, the role of this modification of the silica is to enhance the absorption capacity for CO2 and pre-concentrate it for the further transformation into methanol. So in this graph, we see the enhancement of the modifications of the silica supports with the monoaminated silica and the diaminated silica. And then we focused on trying to study the species of how CO2 is absorbed on these solid supports. And for that, we did solid state carbon-13 NMR. So in this slide, I'm showing the spectra for the monoaminated silica and the diaminated silica. In this first one, these are the species that can form for the monoaminated silica when it captures CO2. So we studied the capture of CO2 in two different conditions, in wet conditions and dry conditions. For the dry conditions, the silica was handled within a glove box, and the NMR rotors were capped inside the inert gas atmosphere. So we were able to obtain a spectrum for the dry conditions. And for the wet conditions, what we did is we left the samples equilibrate in a 100% humidity environment before loading the CO2. So we loaded labeled CO2 with carbon-13, and then we ran the experiments. What we were able to see is that in dry conditions, we have the majority of the species are present as carbamates, which is this rather broad band at 164 ppm. They're seen, and then for the wet conditions, we were able to detect a very sharp signal for the bicarbonate species, which has been elusive in literature. So it's a great finding that we were able to see such clear evidence of these species being formed under the wet conditions. For the diaminated silicas, as we see in the slide, there are many more different structures that can form in the absorption of CO2. So the two up here would be carbamic acid, bicarbonate, and different carbamate species. The spectra are really similar for the diaminated and the monoaminated silica. However, it's worthy to note that we were able to see this shoulder in the wet conditions for the diaminated silica that we attributed to the different carbamate species that form. It's also interesting to see that in the wet conditions, the signals were sharper, and this is attributed to probably pore filling with the water from the humidity that leads to a species being pseudo-dissolved and giving a signal more corresponding to liquid state NMR than solid state NMR. For the same samples, we were also able to get spectra for proton solid state NMR. And we were able to attribute the signals to the different protons and carbon chains. In the case of the diaminated silica, the resolution wasn't enough to distinguish between these three different carbons that are attributed as number 3 in the spectrum, but we can still see some features of the signals that would probably mean overlap of the different signals, but they appeared at similar chemical shifts. So these supports, as I mentioned previously, were used as support for a catalyst. And the reaction procedure is as follows. We load the reactor with the catalyst. We first saturate it with 2 bars of CO2 for 2 hours during the time in the grafted aminated silane chains absorb the CO2 and pre-concentrate it. And then we load the reactor with 75 bars of hydrogen and heat it for 40 hours. During this time, the methanol and different products are formed. And we analyze the gas phase of the reactor through infrared gas phase analysis. So for the gas phase analysis, we use a system, kind of a schematic representation of the system is seen in the slide on the left. So we have an infrared cell, and we evacuate the reactor gases into the infrared cell, and then we run the analysis. A typical spectrum for this gas phase is shown to the right. So we can see the different species that are formed. And we're also able to not only determine what species are formed, but we're able to quantify them. So we did this for the 2 different supports that were crafted. And we were able to obtain these numbers for turnover numbers, which are the moles of methanol produced per mole of the active ruthenium species. So for the diaminated silica, we saw fairly big turnover number conversions. And we didn't only get methanol, there was also carbon monoxide formed during the reaction. When the catalyst has a low loading of this ruthenium species, the selectivity towards methanol seems to be enhanced, but the conversion is lowered. However, as we see in the turnover number, they're fairly similar, so it's still active. And for the monoaminated silica, it doesn't seem to be extremely active, and it's more selective towards CO formation rather than methanol formation. So we know that the support plays a big impact on the activity of the catalyst. So further understanding on how the role of the support in this reaction could lead to better advancements. And then once we understand how the CO2 adsorption influences the reaction system, we can go ahead into more tailored supports, such as carbonaceous supports with nitrogen doping, for example. When we compare our results with state-of-the-art heterogeneous catalysts for these hydrogenation of CO2 reactions, we see that we get fairly intermediately good conversions. However, the highlight is that we're able to do these reactions at lower temperatures, which would be industrially more interesting for the future application of these materials. And with that, I would like to thank my supervisor, Niklas, my co-supervisor, Soltan, members of the group, and colleagues from MNK and the EU Carbon Project.
Okay, Anthony, good. Nice talk. We will wait a few minutes if any questions arise from the audience. We have time for 1 or 2 questions. So I have a question for you, Anthony. Your work is very interesting. Concerning the carbon-based supports, what do you think about it? Could be possible to?
Yes. So from the results we have, we know that the support plays a major role in if the catalyst is active or not. So the pre-concentration step of the reaction seems to be key in the formation of methanol. So once we understand what species are more beneficial towards the formation of methanol from CO2, we could use more tailorable support materials. So from different presentations in the same conference, we can see that carbon is very versatile and can be tailored to many different applications. So we can enhance surface area. We can distinguish different functionalities on the surface. So I mentioned nitrogen doping, for example, which could lead to different ways of sequestering the CO2, to say, if that makes sense. So
okay.
The step of understanding and then further developing.
Okay. So thanks again, Anthony, for your presentation.